And now for the moment you've been waiting for, triple integrals. So similar to the way we define integrals over a two-dimensional region, we may define integrals over a three-dimensional region. So let's just consider a rectangular box given below, where x is between a and b, y is between c and d, and z is between e and f. And we're going to divide the box into L times M times N sub-boxes of dimension delta X by delta Y by delta Z, defined as usual. And that's shown in figure 5.40 of the textbook, which you see here. So there's a box. For each box, we'll call it B sub ijk, we're going to choose a point, just like we normally do when we form a Riemann sum. And then the volume of the box is delta V, which is the product of delta X, delta Y, delta Z, and then form the triple Riemann sum. And so when we take the limit as L, M, and N go to infinity, right? So we make the delta X, delta Y, delta Z infinitely small. That'll give us the triple integral over our region of f of x, y, z dv, provided, of course, that the limit exists. So to compute these integrals, we're going to use Fubini's theorem for triple integrals, which is pretty much the same as Fubini's theorem for double integrals. So if f of x, y, z is a continuous function on a rectangular box B, denoted as the interval AB by the interval CD by the interval EF, then our triple integral over our region here, where our region is the box of f of x, y, z dv, is going to be the integral from E to F, the integral from C to D, the integral from A to B, f of x, y, z, dx, dy, dz. Where, of course, the integral on the right can be expressed in any one of the possible orders of evaluation. So let's do an example. Let's take the integral of 8 times x times y times z over the box B, which is the interval 2, 3 by 1, 2 by 0, 1. So pretty straightforward here. Our integral is going to be, we have the integral from 0 to 1, from 1 to 2, from 2 to 3, 8xyz, dx, dy, dz. And you can test yourself and do it a couple of different ways. Integrate with respect to y first, integrate with respect to z first, whatever you find interesting. Okay, so since I'm integrating with respect to x first, that's going to give me 4x squared yz evaluated at the limits. So I'm going to have the integral from 0 to 1, the integral from 1 to 2 of 20yz dy dz. And so now we're going to integrate with respect to y, and that's going to give us now the integral from 0 to 1 of, we have 10y squared z, evaluate that at the limits for y. And then we're going to get, let me see, that's going to give us the integral from 0 to 1 of 30z dz, which is going to be 15z squared, evaluate at the limits, and finally at the end of the day, I get 15. Awesome. So of course, we're interested in triple integrals over a general region now. So the triple integral of a continuous function f of x, y, z over a general three-dimensional region, we'll call it E, being x, y, z, where let's say x, y is in some D. And give me a second, I'll tell you what D is. And z is between u sub 1 of x, y and u sub 2 of x, y. And this is some region in R3, of course, where D is the projection of the region E into the XY plane. And so that integral is going to be given by It sure is. So we have the triple integral over E of f of x, y, z, dv. That's going to be the double integral over d of the integral from u sub 1 to u sub 2 of our function with respect to z, and then dA. And we can define the integral the same. Similarly, right, if y is given in as on an interval, if y is between two functions of x and z, and xz is in D, and D this time is going to be the projection of our region onto the xz plane. And so similarly, we'll get to our triple integral is going to be equal to double integral over D. This time we're going to be integrating from u sub 1 to u sub 2, but we're going to be integrating with respect to y in that inner integral, dA. So note that the region D can be of type 1 or type 2, as defined when we were talking about integrals in 2 dimensions. And here's a quick example of how that projection into the xy plane would look. And so in this case, right, our integral, for example, would be defined by the integral f of x, y, z, dv, the integral from c to d, if we're looking at the region of the picture, the integral h sub 1 of y to h sub 2 of y, and then the integral u sub 1 of xy to u sub 2 of xy of our function f of x, y, z, dz, dx, dy. Instead of going through all of the possibilities, because there are, a few, should I say quite a few, let's look at some examples. So let's integrate the function 2 times x over the region E, which is the region under the plane 2x plus 3y plus z is equal to 6, lying in the first octant. So a sketch of this is here. And we need to determine the region D in the xy plane by projecting down. And if we project down, right, we're going to get a triangle. So let us draw said triangle. Okay, so let me get some axes here. All right, those look like axes to me. Let me draw a triangle. So our triangle, it looks something like this. Okay, so this is our x-axis, this is our y-axis. This is 1, this is 2, this is 3. This is not to scale. 1, this is 2. So here's where our where we intersect. So how do we check that? Well, if we're projecting down into the xy plane, z is 0. So we're looking at, so the line is going to be given by setting z is equal to 0 in our plane. So the line is given by 2x plus 3y is equal to 6. And that's just for our triangle here. Now, the limits for z in our 3-dimensional region, right, are going to be, well, z is going to range from 0, greater than or equal to 0, because we're in the first octant, and it's going to be less than or equal to just solving 6 minus 2x minus 3y. So we solve for z in our plane here, so we get z is 6 minus 2x minus 3y. And since z has to be, less than or equal to that plane, we get that those as our limits for z. Okay, now what about to integrate over our region D, which is that triangle I drew? What are we going to do? So we have two options. Option number one is to look at the region y, let y range from 0 to 2, and then x is going to be between, solving for that, we're going to get 6 minus 3y over 2. Or we could let x range between 0 and 3, so we could look at x between 0 and 3, and then y is going to be greater than or equal to 0 and less than or equal to 6 minus 2x over 3. Neither one seems to be, like, woohoo, that looks so much easier, so I'm going to choose the first one, but you should try doing the integral using the second one. All right, so I'm just going to choose the first one for the heck of it. So doing that, I'm going to obtain the integral from 0 to 2 for y. X goes from 0 to, well, that's negative 3 halves y plus 3. And z goes from 0 to 6 minus 2x minus 3y, 2x dz, dx, dy. Okay. So then that gives us the integral from 0 to 2, the integral from 0 to negative 3 halves y plus 3. There is no z, 2x is a constant, so I get 2xz, and then evaluated at the limit 0 to 6 minus 2x minus 3y dx dy. So that's going to give us the integral from 0 to 2, the integral of negative 3 halves y plus 3. So we're going to get 2x times 6 minus 2x minus 3y dx dy. Or evaluating that guy in the interior, I'm going to get 12x minus 4x squared minus 6xy dx dy. Now remember, we're next integrating with respect to x. So when I integrate with respect to x, I'm going to get 6x squared minus 4/3 x cubed minus 3x squared y, and again evaluate at the limits dy. Skipping all the algebra, we end up with 18 minus 27y plus 27 halves y squared minus 9/4 y cubed dy. To be fair, I used a computer algebra system to make sure, or to minimize my chance to make a mistake. So the antiderivative here, we get 18y minus 27 halves y squared plus 9 halves y cubed minus 9/16 y to the 4th. That whole sweet thing evaluated at our limits, and after we do all the plug and play, we end up with 9. Phew, all that work just to get 9. Okay, I think that's actually quite enough for this video, so I'm going to hold it right here, and I'm going to put applications and some other things on a second video. So have a great day, everybody. I'm